activation energy, and catalysts. We can represent changes in energy over the course of a reaction with energy profile diagrams, which follow changes in energy levels during reactions. The x-axis is progress of reaction, not time. Reactions may be fast or slow, but to follow energy changes, we do not need to analyze speed. In this example, the energy of the products, right, you go right across here and that gives you the energy, is greater than the energy of the reactants. Therefore, the reaction is endothermic. Energy must be added from the surroundings for the reaction to proceed. To initiate the reaction requires an additional input of initial energy, the activation energy. This energy input relates to the kinetic energy of collisions as well as inputs of energy needed to change chemical bonds. Just as a ball cannot get up over a hill if it does not have enough energy, a reaction cannot occur unless the molecules possess sufficient energy to get over the activation energy barrier. Because of this, energy must always be supplied, so activation energy is greater than zero. In order for a reaction to occur, a minimum amount of energy, the activation energy, must first be applied to the reactants. The net change in energy can be expressed as delta H, the heat of the reaction. The energy peak of the diagram, up here, represents the reactants in their transition state, a transient, unstable, activated complex that exists as products are formed from reactants. Recall that reactions are reversible. Looking at the diagram, from left to right, we see the exothermic reaction, where A plus B yields C plus D. Now look at the diagram from right to left. We see the reaction profile for the endothermic reaction. C plus D yields A plus B. The activation energy for the reverse reaction, from C plus D to the transition state, is much larger than the activation energy for the forward reaction. In this example, energy changes are quantified. The energy of the products is less than the energy of the reactants. Therefore, the reaction is exothermic. Energy will be released to the surroundings. Initiating the reaction requires an input of 50 kilojoules, the activation energy. The net change in energy for the forward reaction, also known as the heat of the reaction, is going to be your final energy, which is 100 kilojoules, minus the 200 kilojoules, or negative 100 kilojoules. Catalysts, or enzymes, increase the rate of reaction by decreasing the activation energy of the reaction. You can see that here. Here's the activation energy without the enzyme or catalyst. Here it is with the enzyme or catalyst. They facilitate the transition state. Catalysts do not change the amount of energy released or absorbed by the reaction. The energy content of the reactants and the products are not changed. Right? Here's the energy of the reactants, and here's the energy of the products. One way a catalyst can speed up a reaction is by holding the reactants physically together in the correct orientation and helping bonds to break. Shown here is hydrogen reacting with ethylene. Both molecules are adsorbed onto the metal surface, which is blue here, which acts as the catalyst. It puts hydrogens, the two hydrogen atoms here, in the right position to bond to the ethylene molecule. Automobiles are equipped with catalytic converters, which are part of their exhaust systems. The exhaust gases contain carbon monoxide, nitrogen oxide, nitrogen dioxide, and unburned hydrocarbons that pass over the surfaces saturated with catalysts. The catalysts promote the conversion of the exhaust gases into carbon dioxide, water, and nitrogen, non-toxic gases. Enzymes are organic catalysts that work in biological systems. They're typically made out of protein. So here's an example. Here's our enzyme, and we have a substrate, and that's the reactants that are going to react together. They enter the active site. And then we have an enzyme-substrate complex, and the reactants are in perfect position to react with each other due to be physically held by the enzyme. The reaction occurs, illustrated by the change in color. We now have an enzyme-product complex. What happens next? The products leave the active site of the enzyme. The enzyme is unaffected and can work on the next substrate. So what did we see? We saw that the reactant in biological systems is called a substrate. The substrates fit into the active site of the enzyme, much like a key fits into a lock. The enzyme then changes shape, thereby lowering the activation energy and speeding up the biological process. Most cells contain several types of enzymes that neutralize reactive oxygen species, which damage biomolecules. An example is catalase, shown here as a component of liver tissue. Catalase converts hydrogen peroxide to water and oxygen.